In this video, we're going to assume that we have a set of data with x's and y's, and we've calculated the correlation coefficient, and it's large enough that we can say that we believe that they are linearly correlated, that they are roughly a straight line, and so we'd like to actually find that line that approximates them. So, we have this picture here, a bunch of data that's close to a line. How do we find this line that is going to kind of fit the data? Now, it's not going to be possible for this line to go through all these data points, right? Because unless our R is exactly 1.0, the data is not a perfect line. If it's not a perfect line, then any line we draw is going to miss at least some of them, maybe even all of them. And we'd like to find some way, well, okay, that's one possible line. What about this line right here? I think we generally would agree that the purple line is a worse way of approximating the data points than the red line was. So how are we going to try to find the best? And how do we measure what does it mean to be the best line? So first off, let's talk about a linear approximation in general. And you may remember from y equals mx plus b from algebra classes. So this is like your equation for your linear approximation. Now, the thing is I'm not using just y here. I'm using y with this extra symbol on it, which we call y hat. And because what that is, that's going to be the estimated value of y. So the thing is, the data point is the actual value of y. Y hat is the estimated value of y. So they're not necessarily the same thing. They're only going to be the same if our line actually goes through that point, which is not generally going to happen. So we need to have two different symbols for them so we can talk about the difference between the actual value and the approximated value. And so the actual value is y. The approximated is going to be the y hat here. And so once you have this formula, let's say the formula you worked out to be would be, 3x plus 5, just making up some numbers here. And let's say your actual data was, 210 here. Well, we would now use this approximation and we would estimate that when you plug in an x value of 2, let's do the little calculation here, 3 times 2 plus 5, we would approximate and get 11 there. So the actual y is 10. The approximation value, the estimated value, in this case y hat, is 11. So once you have your equation, you can plug in your different x's and get your approximated values, your estimated values, whatever you want to call it here. Now, if I want to talk about, how good of an approximation we have, for that we're going to calculate the residuals. And what the residual is, this is going to be the actual y minus the either predicted or estimated y. So for the example that we did right now, the residual in that case, the actual data was 10, the predicted value was 11, so that would have a residual of -1. So that means that one data point is off by 1 unit, and it's actually overestimating, right? The estimate is higher than the real value. It's overestimating it there, off by 1, but that's the residual. Now, when you draw your line, sometimes you're going to overestimate, sometimes you're going to underestimate, so sometimes your residuals will be positive, sometimes your residual will be negative. And so if we want to try to find what's the total amount we're off by, and we don't want there to be any cancellation, what we are going to do is we are going to square all the residuals to make them positive, and then add them up. And this is going to be like the total amount we are off by in some sense. This is, the bigger the number this is, the worse our approximation is. The smaller, the better approximation it is. And guess what? We call this thing least squares regression, because this is going to be the best line that will give the smallest possible sum of the residual squares, so least squares. Okay, and it turns out there's a formula you can calculate for what this line is going to be. It uses calculus, so it's kind of beyond what we're doing in this class. Once again, I'll put it down here, but don't worry about memorizing it. Again, it's something our calculator will do for us. The slope is going to involve the correlation coefficient, the sample standard deviation of y divided by the sample standard deviation of x, and then the y-intercept here is going to be based on the means of the y and the x's, the y bar and the x bar. Those are the sample means of those. And once you have that, then your y has mx plus b is going to give you your least squares regression using that slope and that intercept. So it's actually not that complicated formula, although it does take a lot of work to calculate the r's and the s's and everything. But again, your calculator will do all of that for you. Now I will point out, here's something that your calculator won't do. Once you've found your line here, once you've found your slope and your intercept, you might have to do your own calculation like we did up here to find your estimated point, because the calculator doesn't actually do that part for you. But that one is usually straightforward. Just plug in the x value, multiply times the slope, add the y-intercept. Just keep in mind that is one thing that you might have to do by hand compared to doing all the work to find the slope and intercept in the first place. Now, what do these slope and intercept mean? Well, intercept is the easier one to say. The y-intercept represents the value of the response variable when there is, 0 or no explanatory variable. Now, sometimes this makes sense and sometimes this does not make sense. If you think about the data on age and how much money you're making, the y-intercept wouldn't make any sense. That would be how much money you're making when you're 0 years old. I mean, I don't know about you, but I was not working a job at 0 years old. That would not make any sense in that case. In other scenarios, the value 0 for x might actually make sense. It just depends on the context of the problem. The slope, so the slope represents the average increase in the response variable when the explanatory variable is increased by 1 unit. So thinking back to the age and income thing, that means as you get 1 year older, how much on average more are you going to make? That's what the slope would represent there. So again, whenever you're doing a linear regression problem, one of the things that I will ask of you is to interpret what do these things mean in this context of this problem. So you don't focus too much on doing the calculations yourself. As I said, the calculator will do that for you. I want you to focus on understanding what the numbers mean and what they represent in the context of the problem.